Assalamualaikum, this is me Waqar 32 roll number 18 batch. Welcome to my midterm presentation, the subject chemical engineering reaction. Today's my topic is about temperature dependency Arrhenius law. So let's start the presentation. Today my lecture is about reaction rates and temperature. The rate of reaction rates and temperature. The rate of chemical reaction generally goes up with increasing temperature. The rate constant scale temperature is independent. In this line we discuss about that the rate of reaction also increases with the increasing of temperature, and here K is used for the reactant constant. The overall reaction rate depends upon three kinds: the frequency of collision, the fraction of collision with enough energy to react, the orientation of colliding molecules. Here we learned that when the molecules they collide each other and they lose energy. Now we will discuss about Arrhenius equations. What is the Arrhenius equation? In this slide we will learn. The Arrhenius equation is a formula for the temperature dependency of reaction rates. The equation was proposed by Arrhenius. Arrhenius was a scientist. He proposed a formula in 1889. Molecules only react if they collide each other in the correct orientation. Increasing the temperature increases energy and frequency of molecular collisions. The Arrhenius equation related the rate constant of K to all of these factors. When the molecules collide each other and correctly very proper way to collide each other, and when the temperature increases, they also increase in the molecule collisions. Arrhenius equation gives the dependency of the rate constant of a chemical reaction on the absolute temperature and the pre-exponential factors and other constants of the reactions. Now here is the formula of the Arrhenius equation. K is equal to A into E naught power minus E upon RT, where K is the rate constant and T is absolute temperature when the temperature unit of the Kelvin in Kelvin, as the pre-exponential factor constant for each chemical reactions. E is the activation energy of the reaction in the same unit as R dot T. R is a universal constant, and we know that universal R is the value is 8.134. Now we will discuss derivation of Arrhenius law. Here is the temperature T1, and in the Arrhenius law formula K1 is equal to AE minus EA upon RT. This is equation 1, and temperature T2 for the we will purpose that K2 is equal to AE minus EA upon RT. Here this is equation number 2. Now we will equation number 1 and equation number 2 take a logarithm in both equations. Log K1 is equal to log A minus EA 2.303 RT, equation number 3. Here E is the value of the 2.3030, and equation number 4 also log K2 is equal to log A minus E 2.303 in equation number 4. We will equation 3 and equation number 4 will combine, and we will get a new equations. Log K2 minus log K1 is equal to minus E upon 2.303 RT2 plus EA upon 2.303 RT1. Now we will see that in this equation minus sign is here. Now we will common the temperature in this equations. Here T is common. Then we will change the T temperature. Then we will get a final value of the Arrhenius equations. Arrhenius equation final values is log into K2 upon K1 is equal to EA upon 2.303 R into 1 upon T minus 1 upon T2 bracket. Then we will discuss a problem, and This is the given in the books, and this problem is very simple. The problem is milk is pasteurized if it is heated to 63 centigrade temperature for the 30 minutes, but it is heated at 74 centigrade when it's only 15 seconds for the same results. Find the activation energy of this centralization process. Here is the solution. First of all, to ask the activation energy of a process means of assuming Arrhenius temperature dependency for the process. Now we have given in the questions that temperature T1 is equal to 30 minutes at T1 336 Kelvin, and T2 is given of 15 seconds at a T2 temperature 347 Kelvin. Now as we know that rate of reaction is always inversely proportional to the time. Now here this is the formula we will discuss before slides. Now the formula was the ln R2 upon R1 is equal to ln T1 upon T2 is equal to E upon R into bracket 1 upon T1 minus 1 upon T2 into bracket. Now here is the T1 is 30 minutes and T2 is 15 seconds, but we will convert 15 seconds into minutes. Here 0.25 shows that it's seconds is equal to E upon 8.314, it is the value of the R, and here into round bracket into temperature T1 is given 336 minus 1 upon 347 T2 temperature into bracket is given. Now we will finalize and we will get a simple equation. E is equal to 4.24205 joules per mole. Then we will discuss activation energy and temperature dependency. Here we will see that how temperature depends on the activation energy. The temperature dependency of the reaction is determined by the activation energy and the temperature level of the reaction. These findings are assumed as follows. Here we can determine the temperature dependency with the help of by the determined activation energy and the temperature level. We can summarize and we can find the temperature dependency. From the Arrhenius law, a polar of in K versus 1 upon T and gives a straight line with a large slopes for large E and a small slope for E. Then reaction with high activation energy are very temperature sensitive, and reaction with low activation energy are related to temperature sensitive. In this paragraph we learned that there is a graph and which is straight lines when we react to activation energy with very high temperatures, and any given reaction is much more temperature sensitive and at low temperature than at a high temperature. From the Arrhenius law, the value of frequency of factor K does not affect the temperature sensitivity. Here is the graph. We will discuss about the slopes, and in the previous slides we discussed about that graph. There is a in x-axis there is a temperature and y-axis is a K factor. At temperature slowly decrease and K values increase. Now we were discussing about the graph. Here is the temperature and activation energy graph. Temperature either below the x-axis, the direction temperature will decrease and the activation energy increasing. Here is also a slope, and the slope formula is E is equal to E upon R into K. Here is a high activation energy and low activation energy. Then another is graph endothermic reaction and exothermic reaction. And endothermic reaction energy always absorbs, energy always activation, and exothermic reaction energy is always released. Then another graph is about temperature and activation energy. only a small percentage of collision have enough energy to react. This proportion increases with increasing in temperature. Here, red line shows the higher temperature and blue line shows the low. In the x-axis energy, activation energy EA, and y-axis friction of molecules with energy, and red line friction of molecules greater than the activation energy. Here we see in the graph we are going to see that red line shows the greater activation of energy as compared to blue lines in the graph. Now there is a problem, which is the thermal decomposition of hydrogen iodide. Here we will hydrogen iodide decompose into H2 plus I2. Here are the some temperatures in Kelvins: 508, 427, 393, 356, 283, and also there is the activation of energy K cubic centimoles 0.1059, 0.00301, 310, etc. First we complete the rate of reactions, and we will units of this problem use moles, comma, cubic centimeter and seconds. Solution: first of all, the unit of the rate constant tells that this is second order reactions. First of all, T is equal to K C square into A. K shows the Arrhenius equations. We know that Arrhenius equation K into E power minus E upon RT. Then we will log ln both sides, and we get equation ln K is equal to ln K naught minus E upon R into bracket 1 upon T into bracket. So find the value of rate constant. We will find the K value and K naught and E upon R. We must plot ln K and 1 upon T. The slope gives a ER, the value intercept gives K naught. Let's produce. We will find in this problem K constant. Here is the temperature of the in centigrade, in Kelvin, and 1 upon T Kelvin inverse K and ln K. The solution of this, to find out the value of K, we are going to find the K values. ln K naught is equal to ln K minus E upon R into round bracket 1 upon T into round bracket. Here 5.7764 minus 22.727. We get the value 22.727 by the slopes in the graph. Graph here is showing that temperature is decreasing and ln K activation of energy is also coming to the upside and increasing. When 5.7764 minus into 22.227 bracket into 1 upon 1700 is equal to 38.2439. Here K naught is equal to E. Here is the E is the power 38.2439. We know that E is the power is equal to 4.06 into 10 to the power 16. So for the temperature range covered in the reported data, we were doing that decomposition of hydrogen iodide. Here is the temperature of hydrogen iodide is equal to 4.06 into 10 into power of 16 into E is the power 38.2439 into C square into A, moles per cubic centimeter. That's all. Okay, that's all of my presentation lectures, that temperature dependency from the Arrhenius law, how temperature works in the Arrhenius law, what is the effects of temperature in the Arrhenius law, and we also discuss activation of energy and the relation of temperature with the activation energy. And that's all. This is what I have from the presentation down here. If you have any questions, let me know in the feedback. Thank you.